So now we're going to go through an example problem, and this is fully worked out on OneNote, and it's part of the regular lecture, but it's going to walk through the basics of how to go from an externally loaded torsional shaft to calculate the angle of twist from one side relative to the other. So what we have, I've already copied down the given information here. We're told that we have a shaft with these distances 300 millimeters, 400 millimeters, and 500 millimeters. Made out of steel. It's a constant 40 millimeter diameter shaft, and it has 4 different external torques applied to it. Now for some reason the lettering of these nodes is a little bit off or goofy. It's A, C, D, and B, but we can deal with that. It's not a big deal. So what the problem is asking us to find is the angle of twist of end B with respect to end A. So often the shortcut or the way that we represent that is phi, which means angle of twist, of end B, which we put in a subscript, slash A, also in the subscript, to represent that we're calculating the angle of twist between those 2 different points right there. So if we go over to the solution side, we're going to leave all this given information up and we'll start working on this. Again, the first best thing to write down is going to be the fundamental equation that's going to kind of inform everything else that you do on the problem. So here we're trying to calculate the angle of twist phi. And so our fundamental equation for phi is the integral over the length of the internal torque as a function of x dx divided by the polar moment of inertia as a function of x times the modulus of rigidity. Again, we don't need to use the integral form of this equation here because between each of these points, A, C, D, and B, we have a constant polar moment of inertia, and we have a constant internal torque between each of those points. So all that we have to do analytically is simply break this up into 3 separate shafts, calculate the angle of twist for each of them, and then sum up the results. So we can write this in the arithmetic sum format. It's going to be the sum of TL over JG for each of those segments. All right, so we can get rid of one of these unknowns really quickly. We know that G is a material property, the modulus of rigidity, and we can look that up in the back of the book. And for A36 steel, that is 75 gigapascals, or 75 times 10 to the 9th pascals. That's relatively easy. The lengths are all given to us, 0.5 meters, 0.4, 0.3, straightforward. And the polar moment of inertia, J, we'll be able to calculate that for each of these as well too. That's again a relatively straightforward calculation. This is a solid circular shaft, and so the polar moment of inertia for each of these is simply going to be equal to pi over 2 times the radius to the 4th. And here all the sections have the same exact radius, and so we can calculate one value for all of these. It would be pi over 2 times the radius, which is simply half of the diameter. So it's going to be 0.02 meters. And we'll take that to the 4th power. I don't know if I have that tabulated here or not. I do. The polar moment of inertia for all of these sections is going to be 2.51 times 10 to the negative 7th, and that'll be in meters to the 4th. Okay, so we have G, we have J. So we can basically say we have G, we have J, the L's we just pull straight off of the diagram. So the only real work that we have to do for this problem is to figure out the internal torques. And the previous video that we did, we walked through the procedure of how to do that, so I'm going to go through relatively quickly here. But again, the way that we try to find the internal torques is going to be step number 1, finding out the internal torques. The first thing that I recommend doing for that step is taking this 3-dimensional isometric view and breaking it down into a 2-dimensional diagram that has all of these torques represented as a 2-dimensional vector with double arrowheads. So all that we're going to do in that situation, we're going to draw the shaft in 2 dimensions, and I'm going to start drawing each of these moments on here as 2-dimensional vectors. We use the right-hand rule for that, so we take our fingers on our right hand, we rotate our fingers in the direction of the rotation that's indicated on the 3-dimensional isometric view, And then whichever way our thumb is pointed, that's the way the vector should be pointed on our two-dimensional plot. So here, this 300 Newton meters, I need to turn my hand around to curl my fingers in the direction of this arrow. And so my thumb, is going to be pointed to the right. And so in here, this is going to be a torque vector pointed to the right, and we show it with two arrowheads, and that is 300 Newton meters. We do the same thing for the torque at C, D, and B. We'll see that at C and D, my fingers are following the rotation with my thumb pointed to the left, and so both of those vectors are going to be pointed to the left. That's 500 Newton meters at C, and that's 200 Newton meters at D, and at the end is going to be the same rotation as we saw at point A. So that's going to be a vector pointed to the right, and that is 400 Newton meters. And so let me label each of these points. Again, it's a little bit confusing. It's A, C, D, and B. And so the procedure that I follow for trying to get the internal torque, again, everything that I've shown here are external torques. We don't care about external torques for this equation. This is all internal torques. So we need to go from the external torques and figure out what that does to the internal torques. So I'm simply going to make section cuts in between each of these sections so that I can draw a free body diagram for each. So for section AC, my free body diagram is pretty straightforward. Here's my section cut right here, my internal torque. I will point away from the section cut itself. I have my 300 Newton meter external torque still applied. I'm going to sum the moments. If here's my coordinate system, I will sum the moments about the x-axis equal to 0. And I will find that internal torque AC from this equation is going to be equal to negative 300 Newton meters. So I get the internal torque AC is equal to negative 300 Newton meters. And again, you can write the equilibrium equation out, but fundamentally it's really just these two terms in it. Pretty straightforward. The torque between C and D, it's the same idea. What I'm going to draw for you is the free body diagram. I'm going to not bother writing the equilibrium equation, but you can do it for your own practice if you'd like. My free body diagram, be a little bit longer. My section cut now is between C and D. My internal torque is drawn away from the section cut, and now I have two externally applied torques. I still have the torque at A, which is my 300 Newton meters pointed to the right, but now I'm going to have my 500 Newton meters pointed to the left at point C. I'm going to sum my moments about the x-axis again, equal to 0, and I will find that the torque between C and D is equal to positive 200 Newton meters. And then finally, our last section cut between D and B, I'll make my section cut as easier from a calculation standpoint to keep the portion of the shaft to the right of that section cut. So my free body diagram will look like this. I'll have my section cut. I will draw my internal torque, dB, pointed away from the section cut. And I'll still have my externally applied torque of 400 Newton meters, pointed to the right. Just going to sum up the moments in the x direction, set them equal to 0, and I'll be able to solve for T dB. And I will get that the torque between D and B is equal to positive 400 Newton meters. Okay, so now I have all my internal torques. All right, these external torques, none of those go into these equations. The external torques are just there to allow us to calculate what's happening on the inside. And you'll notice here, it's a common misconception for people to just plug in the values they see here for the external torques. But if you notice, none of my internal torques are equal to 500 Newton meters, right? It might appear just from looking at the external loading that my max internal torque is going to be 500 Newton meters, but it turns out not to be, and that's because we go from negative 300 to positive 200. That's what this 500 Newton meter torque is doing right here, but it never gets a magnitude any higher than 300 or 200 in that section. Down here it goes all the way up to 400. But important to separate your external torques from what's actually going on inside of the member itself. Okay, so we have all of our torques now, so I can check that off the list. All right, pretty straightforward. I'm going to move those over to the right. Torque AC is negative 300 Newton meters. Torque CD is positive 200 Newton meters. And torque DB is positive 400 Newton meters. I copy that over so that I can erase this quickly. And then we're simply just going to go to step number 2. And step number 2 is just going to be evaluating that arithmetic summation equation of TL over JG that we identified as our fundamental kind of overarching general equation. And so now I'm going to apply summation TL over JG. And so if the change in angle of twist between points A and B, it's just the summation of all the changes in angle of twist of member AC, CD, and DB. So this is going to be TL over JG for AC plus TL over JG for CD plus TL over JG for member DB. And again, the signs are important here because you notice here that we have a negative torque, and so this term is going to be negative. These terms are going to be positive. If you didn't get the sign convention right, you might not have them counteracting each other, which is a really important part of this. Another point that I'd mention is that for these, JG is constant across the entire shaft. Same material, same section properties, so I could actually just combine all of these denominators right here, and I would simply get TL for AC, CD, and DB all added up, and the denominator would be a single J times G, J being 2.51 times 10 to the negative 7th meters to the 4th, G being 775 times 10 to the 9th pascals. Again, I'm changing everything into meters and newtons here. Again, a pascal is just a newton per meter squared. I'm going to put the sum of T times L in the numerator for each of these. And so for AC, I get negative 300 Newton meters times the length. AC is a length of 300 millimeters, but we want to change that into meters, so it's 0.3 meters. That's member AC. We're going to add member CD. That has an internal torque of positive 200 Newton meters. It has a length of 400 millimeters or 0.4 meters. And then we add on the effects of member DB, which was positive 400 Newton meters of torque, times the length, which was 0.5 meters or 500 millimeters. Okay, units will all work out. I'll get newtons times meters squared in the numerator. I will get meters to the 4th times newtons per meter squared, which would be newtons per square meter in the denominator, so they cancel out. And my final units for angle of twist will be radians, which is a unitless figure, but we still write radians at the end. And so what I end up with here is a value of the angle of twist of point B relative to point A is 0.01008 radians, which if you want to, you could convert to degrees, but I prefer to stay in radians. But if you want, we can just multiply this by 180 degrees divided by pi, which is a conversion factor from radians to degrees. And in degrees, I would get 0.578 degrees. But again, I want your answers in radians, and you have to recognize that the result of this equation is going to be unitless, but really we write it in terms of radians, which is the same thing. It's kind of like strain, where it's technically a unitless value, but we write the unit on anyway. Okay, so that's it for this problem. Again, the hardest part is simply the statics of it. Bookkeeping as well too. In this one, it's relatively simple because it's all the same material. It's all the same polar moment of inertia, but we have the tools. It's relatively straightforward to have those values vary for each term. Pretty straightforward stuff.